Section 9.2, graphs of polar equations. In this section, we're not really going to do any note-taking. We're just going to get down some examples, some pictures. There's not any vocabulary terms. Well, actually, I lied. There are vocabulary terms, but it's not too terribly bad. So, draft the function. We're just jumping right in. So, number one, r equals the sine of theta. So, how we're going to do this, we're going to use our calculators a lot here in this section. We're going to make some XY tables, and they're not really XY tables because we don't have X and Y. We're going to have theta and R's in our tables, and we're going to use our calculators to help us do that. Before we can use our calculators here, we need to change the mode. Normally we're in function mode, so what you're going to need to do is you're going to need to hit the mode button right there, and it's going to bring up this screen. Okay, you need to scroll down until it's not function anymore. We need to move it over to polar. Okay, once you get there, then when you hit the Y equals button, let me move this over. When you hit the Y equals button, you're going to get a screen that looks like this, where it's not Y1, Y2, Y3 anymore. Now it's R1, R2, R3, and so on. Okay, so I've already gone ahead and typed in R1 equals sine of theta. After we get the function typed in, we need to kind of manipulate the calculator, tell the calculator to manipulate our table so we don't have to scroll a whole heck of a lot. So after you get the function set in, you're going to hit second and then window, and above window you should see the word table set, or the abbreviation for table set, and that's going to lead you to this screen right here, the table setup. The table start, I'm going to say let's make that 0, and the delta table, delta means change in, so basically what are our x values going by, or in this case our theta values going by, and we're going to go in every 15 degrees. Okay, so once you get this screen set up, the table start's going to be 0, the change in table is going to be 15 degrees. Make sure you're in degrees, not radians. And I just realized that I'm in radians, so my table here, when I look at it, is going to be a little bit off in terms of the numbers, but yours, go ahead and switch that to degrees. But once you get the table setup done, and you go to the table, remember that second graph, you should see a bunch of thetas and then the R values. So I'm going to scroll back a page here. So now we've got our original function. I'm going to make an XY table. I'm actually going to make 2 of them just because I'm not going to have enough room. Okay, so I'm going to have, and it's not going to be XY, so the theta is what I'm going to choose, and that's going to leave me with R. Now these values I'm going to get are going to come straight from the table, from the calculator, so I'm not spending a whole lot of time going back and forth between screens. I've already got them written on my sheet. Feel free to pause the video right now and get them copied down as well. I'm going to pause my video as I'm making this, and I'm just going to fill in the first 2 quadrants, and then I'll do the same with the second 2 quadrants, and then we'll pick it back up. Okay, so I've got my table of values here. I skipped 75 and 15, and I skipped 105 and 165. I skipped some of the 15-degree marks. These are the most important ones, and it is important that we have all of these values because with this type of function, it's pretty simple. It's a pretty simple picture. But as we get farther into this video, we are going to need a lot of these theta values because we do need to look at what happens when we go 1 full revolution around the circle. So it is important that we have all of these values in our table. We can't really just kind of do like 0 to 90 because we don't really see the whole picture, or even 0 to 180. We need to do the whole revolution from 0 to 360. Okay, so once we get our table, I'm going to put some of these points on my polar graph. So I have 0, 0, and then I have 30, which is pi over 6. 30 was at a half. So I'm going to make this, let's see, 1, 2, 3. I'm going to make this my 1. So then a half is going to be 2 marks out, which is right there. And then 90 degrees was 1 full one out, so that's up here. And then let's see, what else did I have? 60 degrees was pi over 3. That would be 0.87 or 0.9. So that's really close to 1. So that's like out in here. Sorry for the bell in the background. Let's see, 45 degrees, pi over 4. That was 0.71 or 0.7. So that's a little more than half. Maybe some just short of 3/4, so maybe right in there. And what's going to end up happening is as we move around the circle, this is from 0 to 180, just short of half here, and then right at a half here. What's going to end up happening is that we're going to make a full circle. Now, that's not always going to happen. If I slide back up here, once I get to the second half of the rotation, what's going to end up happening with this one is that these points are going to overlap with these. Okay, so it's not going to be so important, at least in this specific example, that we mark every point, because we're actually going to mark each point twice. But in the next example and the one after that, it is definitely important to have all of those points marked. Okay, so equations with the form. Here's kind of the general note for this little section. Equations with the form R equals a sine of theta, or R equals a cosine of theta will form a circle. Okay, this is sine will be up top. If it's cosine, it'll be something off to the side. Okay, that's kind of just the general shape, and that's something you can see with your graphing calculator. You can also use Desmos. You have to change some settings, but it is possible to do both. Okay, so there's the most basic one: R equals a sine of theta, or R equals a cosine of theta. There's our directions. Now let's try another one here. R equals 6 cosine of 2 theta. Once again, I'm going to pause the video. You should do the same. I'm going to get my table written in, and then we're going to go from there. All right, so when I get my thetas in there, I used radians this time. You can still use the degrees in the calculator. This would be 0, 30, 45, 60, 90, 120, 135, 150, 180, along those lines. I just chose radians this time because my unit circle here is in radians. So what I'm going to do next is I'm going to put these points on the graph, and I'm going to try to stay in order, and it's going to be important that we stay in order. So my unit circle here looks like I have 1, 2, 3, 4, 5, 6 marks here, so I'm just going to think of this as my outer edge of 6. And let's go ahead and put these points on the graph. So at 0 degrees or 0 radians, I am at an R value of 6, so that's right there. At pi over 6, we were at 3, so 1, 2, 3 is there. At pi over 4, that would be at 0. Let's see, make that a little bit bigger. At pi over 3, we were at negative 3, so remember, pi over 3, we're going the opposite direction since it's a negative. So negative 3, let's see, 1, 2, 3 should be right in there. I'm going to slide this down just a touch. Okay, at pi over 2, we were at negative 6, so that's actually going to be way down here. At 2 pi over 3, that was negative 3. So 2 pi over 3, negative 3 should be right in there. 3 pi over 4, we're back at 0. 5 pi over 6 is positive 3, so 1, 2, 3 is right there. At pi, we were at 6, so that's way out there on the edge. 7 pi over 6, we were at 3, so that is there. 5 pi over 4, back at 0. 4 pi over 3, we are at negative 3, so we're just going to go at 4 pi over 3 and work our way backwards. So that's going to be right in there. 3 pi over 2 is negative 6, so that's actually going to be way up here at pi over 2. 5 pi over 3 was at negative 3, so that's going to be right in there. And 7 pi over 4, we're at origin. The origin again, 0. 11 pi over 6 was a positive 3, so that's there. And then at 2 pi, we're back at 6. So, whoops, we are back right here at 6. So the question is, what does this thing look like? And this is why I say we have to follow the order. We're going to connect the dots here, but we have to go in the order that we mark them in. Okay, it's not just a matter of drawing random lines here. So we're going to start back here at 0, and we're just going to follow the order of points. So we went from here to there, and then back around, and then we came up to here, then we went over here, back up one more time all the way up to the top, and then one more lap around. This is our picture. Now, if I did this a little more accurately or with some technology, these points should all intersect at 0. Now, I'm not the greatest artist, so we're just going to kind of make the best of it. So, equations that look like this. So something like 6 cosine of 2 theta. So let me write this in here. Equations of the form R equals A times the cosine of n theta, or R equals A times the sine of n theta, where n is a positive integer, are called roses. Okay, that's the vocabulary term. These are roses. It kind of looks like a different type of flower, but rose is the term that is used. Okay, the biggest thing here, as n increases, as this number next to the theta increases, the number of petals increases. And like I said, when we're graphing, make sure we follow the order of the table to ensure the correct shape. Okay, so with this note right here at the bottom of the screen, as n increases, the number of petals increases. I've got a picture here from Desmos to kind of show you. As this number next to theta gets bigger, so the blue one here is the really lots of petals, the red one, a little bit bigger. As the n value gets bigger, the number of petals or the number of little flower leaves it increases, and you'll see that whether you use sine or cosine. So these are the roses. I got another type of function here. Once again, I'm going to pause the video. I'm going to make my whole table, and then we'll pick it right back up. Okay, so in this picture, in this table, I went back to degrees, and my picture here with the polar graph paper is still in radians, but that's okay. We still know how to convert between radians and degrees. So let's put our points on the graph. So we had 0, 2. This time, let's see, my biggest R value here looks like 6, so I'm going to have to go just by ones again, so 6 will be way out here. So we got 0, 2, so that was right here. And then we have 30, 0, so that's at the origin, or the pole. 45 was at negative 0.83, so that's going to be roughly right in there. Now my pen's a little wide, so it's going to be kind of hard to draw this when we're working with smaller numbers, but pencil or a fine pen would be probably a little better. 60, negative 1.5, so that's going to be right in about there, if I can get my pen to draw it, and skip that, right in there. Negative 90 was at negative 2, so that's right there. Negative 1 or 120 was at negative 1.5, so that again is right in there. 135 was negative 0.83, so that's somewhere in that vicinity, right in there. 150 was at 0, so I'm back at the pole. 210 was at negative 4. Actually, I missed 180. That was at 2. That's right there. And then 210 was at 4, so 210 was, let's see, 210 is 7 pi over 6. So that's at 4, so that's right here. And then 225 was at 4.8, so almost 5, right about in there. 240 was at 5.5. So let's see, 240 was, that's 4 pi over 3, so that's 5.5. 270 was at 6. 300 was at 5.5, so that's right there. 315, 4.8, so just inside the blue line there. 330 was at 4, and the last one, 360, we're back at 2. So again, we have to follow the order. So that goes like this, and then it came back around.
Middle school staff will take a 5-minute break. You can be to the other.
And we have our picture. Now, I didn't quite start at the right place. I should have started here, but it's the same shape. It goes all the way around, makes that little loop in here. Pictures like this have an interesting name. They are called limasones. Limacone, and technically I can't draw this accent mark, but there's a little accent mark on the bottom of the C. Okay, bottom of the C. It's pronounced limacone. L-I-M-A-C-O-N. Limacone. Okay, equations of the form. The form is R equals A plus B cosine of theta, or R equals A plus B sine of theta. They're called limasones. Okay, they have that little. They kind of look like a P or like a buckeye with the little thing in the middle. Okay, if A equals B. So in my example here, I had 2 and 4. So these two numbers were not equal to. If they are equal, okay, if A and B are the same, like 2 plus 2 sine of theta, or in my example here I've got, you can see 2 plus 2 cosine of theta. If it's going to come, the numbers are the same, it's not going to make this little loop in the middle. It's going to come right to a point and make a dimple, okay? And it's going to look like this. These little images, these pictures are called cardioids. It's another vocabulary term. It looks kind of like a heart. Because, you know, cardioid, like cardiac, which references the heart, kind of makes a little bit of a heart shape. Whoops, that should have been the pointer. Kind of makes a little heart shape. So cardioids are a heart. Limasones have the loop in the middle. Looks like a cardioid with a little loop cut out or something along those lines. The other two classical curves, and I'm not going to go through the whole, make a table and all that. There are two other classical curves. The first one is called the lemniscate. Lemniscate. Let me try to L-E-M, lemniscate. Lemniscate. Okay? These occur when the equation is r squared equals, the book says a cosine of 2 theta, or r squared is equal to a sine of 2 theta. Now the key here, when you want to graph it, you have to get r alone. So you have to take the square root of both sides to get r by itself. the shape here is like a figure eight or the infinity sign. I've got a couple of pictures here of what lemniscates are. It kind of looks like an airplane propeller almost, or like a figure eight or an infinity symbol, anything like that. The purple one is if you have sine. Sine is going to be a little more diagonally based. Cosine will be more horizontally based. Those are lemniscates. Okay. The last one is the spiral of Archimedes. Okay, this one really doesn't end. It doesn't make a nice loop like these do, or the limasones, or the cardioids, or even the circles, or the roses. This one just goes on forever. The spiral of Archimedes. This happens when the equation is r equals a theta, and the key here is that the theta has to be in radians. If it's not in radians, it's not going to work. The angle has to be in radians here. So you can see in my picture that I've got my angles are in radians. This gets really big, really far out from the pole really, really fast. Okay, so I've got a picture here, r equals 2 theta. If I went 3 theta, you'd hardly see anything. It would just go really spiral really fast, really wide. So we're not going to do something terribly big. We're not going to spend a whole lot of time graphing lemniscates or the spiral of Archimedes, but the book does touch on it just a little bit.